All right, finishing up that example. Y equals 9, add x equals negative 1, which is a fancy way of saying you got a dot at negative 1 comma 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now remember, the limit from the left and the limit from the right of a function like this is the same thing. For a, the limit from the left is using the 3x because this is the line that we have to use. Okay? So from the left, it's negative 3. And from the right, we're still using that same line. And again, you can plug straight in because there's no domain issues. So what's the limit as x approaches negative 1? Well, it's when the left and the right limits are the same. Well, they're the same. They're both negative 3. So that's what the limit as x approaches negative 1 is. Now here's what a lot of students have trouble with. They never use the 9. They never said any of their answers were 9. And then they want to include that 9 somehow. But again, that 9 is a rogue point that has no bearing on limits. So don't use it. All right, now keep in mind that we didn't have to graph this to figure out that last example on the notes. All you had to recognize was the functions that's not equal at a certain point is the function that we use every time from the left or the right. All right, last example. What do you do when you have piecewise functions? I'm sorry. What do you do when you have an absolute value function? You turn it into a piecewise function, which I showed you how to do in the graphing sense chapter. So, how do we turn absolute value functions into piecewise? We get critical numbers from the place that makes the absolute value 0. Okay? So when I say absolute value critical numbers, I'm saying x minus 1, you're setting that thing equal to 0, and that gives you your first critical number. X equals 1. Then you ask yourself, when x is less than 1, I think we talked about from negative infinity to infinity, but I'm pretty sure we probably just did this. When x is less than 1, and when x is greater than 1. This function is going to have a particular type of behavior which changes for this absolute value component. So what you do is you say, pick a number but that's less than 1. 0. When I plug 0 into this right here, what is the behavior of that absolute value function? So plug in 0 right here. You get -1. If it's a negative number, then that means that the absolute value quantity behaves like the negative of that quantity. So, the top is not nested in absolute value bars. It doesn't change. The bottom yielded a negative number. So you're going to say that's -x plus 1. Over here, test a point that's greater than 1. Try 2. 2 minus 1. That's a positive number. That means everything nested in the absolute value bars is going to yield positive behavior of x minus 1. So again, the top is unchanged. The bottom, still x minus 1. So here's what it looks like. This is 1 minus x over, you know what? I'm just going to call this positive 1 minus x. You'll see why in a minute. And this is 1 minus x over x minus 1, where x is greater than 1. Notice I'm not putting an equal to on either of these because it's in the bottom part of a fraction. So you just straight up can't equal 1 at all. That's why there's no equal to. All right, these can simplify. Anything divided by itself is 1. So it equals 1 from the left of 1. That's kind of weird. And then I don't know if you noticed this, but this is technically -x plus 1. Which, if I took a negative out of the top, would be -x minus 1. The bottom's -1. Okay. This is the piecewise representation of that absolute value function. So which one represents behavior from the right? Because it's saying, what's the limit as x approaches 1 from the right? It's this one. So the answer is -1. All right, here's the last example. All right, so let's get the piecewise out of this. Looks like 7 minus x is inside the bars. So where does that equal 0? At x equals 7. So there's going to be a point where it splits off. When x is less than 7, it's going to have certain behavior. When x is greater than 7, it's going to have certain behavior. Since it's on the bottom part of the fraction, I'm not putting equal to's to create a filled in hole. It's just going to be an open circle there. So let's try 0. When you plug in 0 for 7 minus x, you get a positive number. So we're keeping it as a positive. So it's 3 over 7 minus x. For the other part, let's try something like 8. What is 7 minus 8? -1. It yields negative behavior inside the absolute value bars. So this one is going to be 3 over negative 7 plus x. And I'm just going to write it as x minus 7 on the bottom. I think it's easier to visualize that way. Now, let's just, from the get-go, only pay attention to what needs to be paid attention to. The limit as x approaches 7 from the right. We are only taking into consideration this, because it's the one that's describing rightmost behavior, right endpoint behavior. Oh, this is just like the ones with the infinity symbols, remember? We can rewrite this as 1 over x minus 7. The limit as x approaches 7 from the right of 1 over x minus 7 times the limit as x approaches 7 from the right of 3. Okay? So we're going to have an infinite limit here. We haven't asked them to. So if you'll recall from earlier in the notes on one of those previous videos, from the right is going to be positive infinity. I can't plug 7 in anywhere. That just means it's 3. So it's 3 times infinity. All right, hey, this is a lot to digest. I'm giving you guys an entire week of working through the problem set. All right, so try not to get discouraged. Ask help for when you can. I'm gonna try to put some more videos on Google Classroom to give you guys some more guidance. But yeah, just work on it, and good luck. Thanks.